Yeah, my name is Nastali Catherine, and I'm going to take you through machine learning with my friend Loganzi Matthias. So let's dive. What is machine learning? It is a field of study that gives computers the ability to learn without being explicitly programmed. We are going to look at two major types of machine learning, the supervised and the unsupervised. So supervised learning, here the models learn from data. It is trained on input-output pairs, then it makes predictions on new data. They basically get labeled data, and this model learns from it. Then it is given a new sets of data, and it comes up with predictions on that new data. You could say under supervised learning, there is a linear regression, logistic regression, the SMVs, decision trees, and neural networks. The advantages is that it provides accurate predictions with high quality data, suitable for real world situations. And yeah, so I want to look at unsupervised learning, which involves training data on unlabeled outputs. So it learns patterns, it finds patterns within the data, such as clustering or through clustering and dimensionality reduction. So in unsupervised learning, you could say in clustering, it finds similar data points. Then in dimensionality reduction, it reduces the number of variables or features in a data set. That would be, in an example, PCA, which is principal component analysis. So in the algorithms used in unsupervised learning, we could say there is k-means clustering and hierarchical clustering. Yes. So the advantages we have here is that it is useful for exploring data structure, and it can cover hidden patterns. It uncovers hidden patterns in data. The challenges we would have here is that it results to being harder to interpret than in supervised learning, and the success depends on the feature selection. Yeah. For unsupervised learning, you could say you have to have high quality data for your module to be accurate, and it needs large sums of data. Yeah. So now I want to look at a model. What is a model? A model itself is a representation of a phenomenon. It predicts, classifies, and finds patterns. That is it. So it represents relationships, the features, which are the inputs, and the outputs, which would be the labels, how they are understood and how they are expressed. So it's the backbone of any predictive or decision-making system. Then we want to see the deterministic models. They work with fixed relationships, inputs and outputs without any randomness. Then we have the probabilistic models, which acknowledge uncertainty and randomness using the functions. Now here, in deterministic, they are direct. They assume no uncertainty or noise in the system. They are suitable for systems whose behavior are fully predictable. For example, you could say we have linear regression. Yeah. And the mathematical modules, you could say the Newton's laws of motion. They are direct. Now, they are simple to interpret and compute. They work well with scenarios with minimal randomness or variability. Then, under the probabilistic, you could say they incorporate noise. Yeah, they do what the others don't. They incorporate noise. They have a measure of confidence in their predictions. You could say under the probabilistic, we are going to see that we have the components, the deterministic part and the random error. So it predicts the outcomes based on fixed rules. Then the random error accounts for the variations and the uncertainties in the predictions. You could say y is equals to a function of x plus epsilon. Now, epsilon would be the random error that would occur in our formula. Now, under these examples, you could say we have regression models and the types of probabilistic models. Now, we want to look at the regression models, which represent the relationship between the dependent and the explanatory variables. What would you say about regression models? We have steps. when modeling it, we hypothesize the deterministic components, then we specify the probability distribution of the random error, we evaluate the fitted model, then we use the model for prediction and estimation. Now we have linear regression. They assume a linear relationship. Yes, when you look at linear regression, we would say that it's a statistical method that uses the relationship between a dependent variable, the outcome you want to predict, and the more independent variables, which are the factors you believe are influencing the outcome. And we would have simple linear regressions, which involves one independent variable, or multilinear regression, which involves two or more independent variables. So the model itself tries to best fit, to find the fitting plane or the hyperplane, which represents the relationship between the variables. Now we have the least squares method that we are seeing here. It finds the best fit line or the plane that the best summarizes between the values and their the dependent variable and the values within it by the model, how it predicts them. So you could say it calculates the residuals, squares them, sums them, then finds the best fit depending on the plane. Now we want to look at parametric versus non-parametric models. The parametric models are predefined models, like how you see in linear regression. Yes, you could say they rely on a fixed number of parameters to summarize the data. Now we want to say that if you have linear regression under the parametric models, then under the non-parametric models, there are no strict assumptions and the model adapts based on the data, which means it finds the assumptions under the structure, the underlying structure, then finds the unknown relationships between the data. What it does, what would be the key characteristics of non-parametric models? They are flexible. They have no fixed number of parameters. They are data-driven. Yes. So under non-parametric models, you could see here things of KNN algorithm, decision trees, and the canonical estimation. So I'm going to look at the k-nearest neighbors. And the k-nearest neighbors is an algorithm in machine learning, which is a simple and non-parametric method used for classification and regression. You could say it calculates the distance between the training data and the test point. Then it finds the nearest neighbors based on a distance, then classifies which point using a majority vote. We shall use the picture in the corner to explain more on that. When you talk about finding the nearest distance, we shall hear things of the Euclidean distance, which features measure on similar properties. Then we have the Manhattan distance, which measures features based on dissimilar properties. Now we have feature scaling, which normalizes features if they are on different scales. And we could say this KNN algorithms is used in text mining, finance, agriculture, and many others. So we want to look at this data that we have here. Example in the picture. This gray dot is our test subject. Is the data we want to classify. So we say there are three potential classes, the yellow, the green, and the orange. And so we calculate the distances between the gray dot and all the other classes, all the points that we have here in our plane, and you realize that the distances are here. They are placed in order according to the one that is nearest, so that is ascending order. Now we vote on the labels. We vote which ones are nearer to the gray dot. We have two of the yellows, of the class yellows, are closer to the gray dot, our test, compared to the green and the orange. So this gray dot is then predicted to be of the yellow class. What would be the advantages of this KNN algorithm. It is easy to implement. There are no assumptions about the data distribution. But regression, and it works for regression and classification. It is suitable for multi-class problems. It is slower with large data sets, and skewed classes can dominate predictions. It is sensitive to missing values and feature scaling. I'm going to hand over to my counterpart, Luganzi Matthias. Okay.
Hi everyone, my name is Uganzi Matthias Joseph and I'm teaming up with Nasari Catherine. In this video I'm going to be explaining decision trees, assembled learning, random forests, k-means clustering, subvector machining, and then a principal component analysis. Decision trees refer to like structures in machine learning and they are to visualize and make predictions based on a series of decisions. You can think of a decision tree as a tree having a parent node and branches having the children. Each node represents a decision and a branch represents a possible outcome. The metrics of a decision tree are entropy and gene impurity. Entropy measures the level of randomness in the data, so that high entropy indicates greater uncertainty in predicting the class of a data point. The gene impurity measures mislabeling frequency. These elements are randomly selected, so gene impurity helps us to know the probability of misclassifying an element if it were randomly labeled according to the class distributions. Then we have pruning. The tree pruning is a technique to prevent overfitting by simplifying the decision tree. In this way that we trim off branches that are unnecessary during the tree search. It has two methods, the pre-pruning and post-pruning. The pre-pruning limits the growth of the tree during the training process, and this has three methods: the max depth, and then which we can call the maximum depth, and which this sets the limit of the number of levels in the tree. And minimum sample split sets the minimum number of data points in a node before allowing a split. And the minimum sample leaf limits the number of data points in a leaf node. And then you have post pruning. Post pruning allows the tree to grow fully and then prunes it back. This as a precaution. And then we have decision trees, pros and cons, which are advantages and disadvantages. Simple to interpret and visualize, capture nonlinear pattern easily, then minimal pre-processing. Minimal pre-processing, since data is sensitive. In this case, they can handle both categorical and numerical features without the need for extensive transformations like normalization. That's the minimal pre-processing. Then you have the cons, sensitive to noise and imbalance in data. Due to sensitivity in data, small variations in the training data can lead to significant changes in the structure of the tree, results making the results unreliable. Then variability in trees. This is still due to sensitivity. Changes in data decision tree can exhibit high variancy. Then to move on to assembled learning. Assembled learning is a technique that combines multiple models to create a single stronger model that improves performance and accuracy. This can be done through leveraging the strength of different models and mitigating their weaknesses. Assembled learning methods can simplify, improve prediction accuracy, robustness, and generalization. It has three methods: bootstrapping, bagging, and random forests. Bootstrapping is a training of models sequentially, where each model focuses on the example that were misclassified by previous model. Then bagging is a training of multiple instances of the same model or different subsets of the data and then combined their prediction through voting. That's more like the average, finding the average of their prediction, which leads to robust results. Then we have random forests. Random forest is like a collection of decision trees. Instead of relying on simple decision trees, we can prone overfitting, which are prone to overfitting. We can use random forests to combine the prediction of all decision trees within. So random forest, in a layman's language, is like combination of decision trees. And steps to get to generating it, we have building multiple decorated decision trees, randomly select features for split, and then assemble output from all trees. Then random forests have pros and cons. The pros are work well in large datasets, reduced risk for overfitting. Then we have robust outliners and nonlinear patterns. Then the cons are slow training, especially in high dimensional categories. Uh, then we have support vector machining. Support vector machining is a machine uh, in machine learning, a supervised learning algorithms used for classification and regression tasks. Support vector machines aim to find the optimal hyperlane that best separates data points belonging to different classes. The optimal hyperlane is the one that maximizes the margin between dataset points of each class. As you can see in our image here, we have two support vector machines, which are green and blue. We have the positive hyperlane and the negative hyperlane, and then we have the maximum margin combining the two hyperlanes. um, Basically, we have the gamma hyperparameter. In this, we have the lower gamma and the high gamma. The lower gamma breaks the similarity in the radius, meaning that each training example influences a larger region of data space. The high gamma narrows the similarity radius, meaning the examples will be trained with have a smaller influence, focusing on only the data points very close to them. Then we have k-means clustering. K-means clustering can be an unsupervised learning machine learning algorithm used to group data points to k clusters based on their similarity. As you can look in our image here, before class k-means and after k-means, one has scattered data points and one has grouped points depending on their classification. It works by assigning each data point to the nearest cluster center and updating the center iteratively until the cluster stabilizes. It has weaknesses. The weaknesses are sensitive to outliners, lies on predefined cluster count. Initial cluster centers influences outcome, and it has the strengths which are easy to implement and popular, effective for hyper-explored clusters. Principal component analysis. Principal component analysis is an unsupervised machine learning technique used for dimensionality reduction. In simpler terms, PCA is like a statistical procedure that transforms a set of correlated values into a new set of uncorrelated variables called principal components. These components are ordered in a way that the first principal component explains that most variant data, and second explains the second most variant data, and so on. As you can see in our image, those close to the line blue are more variant than those far away from the line. Applications of this would be image compression, facial recognition, and preprocessing for cluster regression. Then limitations are assume linear correlation. Assuming linear correlation is in a way that when you use PCA, it assumes the relationship are linear, hence not being uh, efficient on nonlinear relationships. And then scaled variables can yield varying results. Variables with larger scales can dominate the analysis even if they are not important. That's all about this course, and these are certificates you are able to retrieve from ISON Educator, where we undertook a diploma in machine learning.